Okay, here we go. 7-4. This one is about parallel lines and what happens when you start cutting into polygons and things with parallel lines, and what happens in terms of similarity and proportional stuff. All right, so the first one's about triangles. If you have a random parallel here, it's parallel to one of the sides of the triangle. That creates, of course, similar triangles. If you look closely here, we'll have corresponding angles here at B and C, or you could even say corresponding angles here at E and D. If that's not enough for you, we, of course, would have angle A in both triangles. So we would say not only is triangle ABE proportional or similar to ACD because of angle, we would say stuff like AB over AC would be equal to AE over AD. But notice that's not exactly what they do here. They go one step further. They kind of say, and it's a little bit, I don't know, feels like it might not be true at first. Feels like it might be a little bit illegal, what they are actually saying here. They're not saying that AB is to AC as AB is, or sorry, AE is to AD. They're saying actually that AB is to BC as AE is to ED. Now that's a little weird because this little X right here, and is that an X? Yeah, okay. And this little Y right here are not actually sides of the triangle. Let me put an A and a B here. What we're actually saying here is A over X equals B over Y. And it turns out that it actually works out. Due to some fancy subtraction and some laws of algebra, that actually works out that you can kind of subtract this A and B off of the full sides that we would have down here, and this actually works out. Of course, since this proportion works, you can kind of do it sideways. You could say A over B equals X over Y. The problem with this is it's really easy to accidentally say, okay, well, that's the same thing as C over Z, and it's really not. C over Z does not fit into this system. And we'll talk about, well, I guess I can talk about Y right now. That doesn't work because C and Z, especially the Z is a big side of the figure. Z is like this thing down here. It's that full side. And yes, it's proportional to BE the same way all these other sides worked. So these altogether are all fractions that are not equal to these, if you notice carefully. So we can't put that in there. And it's very tempting to accidentally make that mistake. I'll bring that up as we get into it. Okay, so state whether this is true or false. Well, okay. So what we just learned here is that the new one here is this little FH goes with HA like FT goes with TB, and that's kind of the new one. All the other ones about similar triangles are also true. FA, let's look at this. FA is to HA, FA, so full side to bottom part equals full side to bottom part. Never had that one. Not legal. Full side and bottom part, that doesn't work. The bottom part can really only compare to, like HA, I can really only link up with FH. I can't link up HA and FA. FH is to FT as HA is to TB. Also false because FH is to FT, FH, FT, okay. HA and TB, that's, oh wait, I'm sorry, that does work. FH, HA, FT, TB. Yeah, sorry, I was looking at HT, it wasn't HT, it was FT. This is true. This is from the new rule. It's just sideways as compared, oh, I did part 2 next. It's sideways as compared to the one on the previous page, but that's okay. FH is to AB. Ooh, that looks really crazy. How are we going to compare FH to AB? This is a little side of the little side of the little triangle. This is a big side of the big triangle. I don't think these should go together at all. AH, oh my gosh, that's completely ridiculous. I'm not even going to keep reading that. FT over FH, okay, equals FB over FA. Sure, this is good old similar triangle stuff. FA over FH, so full one to top thing equals FT, wait a second, over T, no, that's all twisted up and backwards. FA is in the big triangle, FT is in the little triangle, and it doesn't even correspond, so that doesn't work. Remember, in these, if you kind of look at this as row and columns, each row and each column has to kind of hang together in some way. Like, sometimes we'll use one row for one triangle and the other row for the other triangle, or one column for one triangle and the other column for the other triangle. And it has to correspond, and it has to line up. The other thing is the two different sides and the two different triangles kind of have to make sense. These false ones here don't make any kind of organizational sense. All right, next one, FA, which is full side over here, is to FB. Okay, so that'd be like this big side is to this big side. The other one should look kind of the same, like FH to FT, that would work. But they're saying FA to FB equals HA to TB. Now, didn't we see that one already? No, you can't compare big sides to bottom parts. That doesn't work. You can compare big sides, you can compare big sides to small sides of the triangle, but HA and TB aren't sides of the triangle. The only thing you can really do with HA and TB is what we just learned about in this one here. You can compare those little cut-off parts at the end to the parts that they were stuck onto, but that's it. You can't compare them to the full side. I can't do X and CA. That's not going to work in anything. All right, solve for missing variables. All right, so the new one we just learned was something like 10 over y actually equals 8 over 12. When you're doing those, though, I mean, it's a little bit dangerous because this ratio here, whatever these are, the 10 over y and 8 over 12, that equals like 2/3 or something. That's not the enlargement factor of the little triangle to the big triangle. We'll see what that is in a second. I just want to get this one out of the way here. So 10 times 12 equals 8y. Oh, I probably should have reduced this fraction first, but I didn't. So what's 120 divided by 8? 15? I hope that's right. And then the other one, yeah, this x here, I'm going to use x as a side of this triangle, so I have to compare it to a side of the big triangle. X is a full side of the little triangle, so it goes with a full side of the other triangle because that's what I'm going to use to compare it to. And I'm going to use 8 and 20 to compare that. 8 is to 20 as x is to 24. You know what, this time I'm going to reduce my fractions first, make my life easier. I didn't like all those big numbers. So 5x equals 48. So x is almost 10. We're just going to leave it like that. Okay. Be careful here. I made a mistake in the last video. Sorry about that. Did you find it? Thinking about trying to figure out how to make an annotation in the YouTube video and point out my mistake so that if anyone else watches this video for test review, they see that it's a mistake. Okay. Well, if a line intersects two sides of a triangle and separates the sides into proportional corresponding segments, then the line is parallel to the third side of the triangle. So this, really all this is the converse of the last one. Notice that's why it's called converse. We'll zip these together as a biconditional. This is a way for being able to tell, are those things parallel? And we'll use the numbers, and that's what this example is about. If this proportion works out the way it should have, then I can tell lines are proportional. So if this, see, because there's no variable in here, I can just try to compare it and see if it works. Is 6 over 9 equal to 8 over 10? Whoa, over 10. And if it is, if this is true, then it will tell me that the lines are parallel. I'm going to reduce these fractions. This is 4/5. This one is 2/3. Is 2/3 equal to 4/5? No. So these are not parallel. Okay. Mid-segment of a triangle. This reminds me of the mid-segment of a trapezoid. It's not like median. It connects midpoints, but it connects from a midpoint to a midpoint. Well, if this happens, this is just really a special case of what we've just been looking at. Because I know this has to be parallel because these are proportional. They're both in the ratio of 1. And this stuff that they tell us here in this example is kind of not very profound. The most profound thing is actually on the last page. This is just a special case of that. And I guess the definition of mid-segment. Oh yeah, here's the thing that's kind of cool. The thing that's cool is we get half here. So this JK is half of FG. The little triangle, because we know this ratio is equal, we know that HK is half of HG. That means that the ratio of the length of the little triangle to the ratio of the length of the big triangle is always half. So JK is half of FG, and I'm serious. So let's do some of those. So we got some mid-segments here. We have 2 of the 3 mid-segments drawn in this triangle. They didn't draw a DE, but that's okay. So I know if DF is 9.2, that tells me that BC has to be, oh, they didn't draw this in here. Why didn't they ask for this? I know that BC has to be 18.4. It has to be double of the thing that's parallel to it. Likewise, if, if AC, where's AC? Okay, so AC is 15. If this whole thing is 15, then if I drew in DE here, this would have to be 7.5. What are they asking for? E to F? How am I supposed to find E to F? I don't know if that's possible. Oh, C. All right, E to C. Well, E to C is half of 18.4. E to C has to be 9.2. That is because it's the midpoint of this thing, and I already know this is double this. Well, look what happens. What ends up happening here is that this little segment E to C is congruent to DF. So actually, these 3 segments are congruent. That's 1 tick mark. These double tick mark segments are the same as this one, and the triple tick mark, and that's the same as this. But how on earth am I supposed to find EF? Oh, wait a second. Yeah, AC is 15. Great. I don't know AB. I don't know EF. I have no idea what this is. Unless this is a misprint and this was supposed to say AB. I don't know what EF is, so I'm guessing that's a misprint. So we'll figure that out. All right, triangle DBF. Sorry, angle DBF. Notice that this was a mid segment here because this connects midpoints, and there it makes it so this has to be parallel to this one. And because those are parallel, we're going to have corresponding angles here and here. So that makes that 86 degrees. All right. Okay, a couple more things. Oh, actually, this is our first corollary of this chapter. Theorem 7.7 was about, just so we know what we're talking about here, Theorem 7.7 was the one about the midpoints and making this length half as long as the side of the triangle. You can kind of broaden this out a bit and say, if you just had generic parallel lines in the first place, and it makes, we have different transversals across those, we're going to have these little subparts of, you can imagine a bigger triangle here. The parts that it cuts off are going to stay in proportion all the way down that triangle. So even though it's not connected as a triangle here at the bottom, the things are still in proportion. So if all these are parallel, then the ratio of this part to this part is going to equal the ratio of this part to this part. X over Y is going to equal W over Z. It kind of looks like a little proportion the way it's written here with a fraction bar and everything. So that's pretty easy to remember, especially if it's horizontal parallels like this. Those aren't the only two that can be written. You could write some more. We don't really know about the proportional lengths of things like CG or BF or AE, but we could write X over, so the way they did it here was X over Y equals W over Z. The other ways to write this would be kind of like sideways. X over W would equal Y over Z. Again, the one they wrote here was X over Y equals W over Z. Could you write another one? You could turn it upside down, I guess, or turn this thing upside down. We could say W over X equals Z over Y. There's lots of ways to do that. As long as you know on the next step, the cross multiplying is going to lead to the equation X times Z equals Y times W. All right, I might be able to finish this in one video. I got 2.5 minutes. All right, if the scale factor is 1, in other words, if this is the line parallel in between these that contains the midpoint every time, it's going to, or the midpoint on 1, it's going to keep continuing to carry midpoints. So in other words, again, if all these are parallel and B is the midpoint of AC, then F is going to have to be a midpoint of EG. In other words, yeah, and if we do another transversal later down here at a completely different angle, like that or something, and these lines all continued, that midpoint would be here among these ones like that. Okay. All right, so last picture. So find X, and this is exactly what we're doing. Oh, it's quadratic time. Let me do the setup. Pause. Well, these are, this would be how the proportion works, but this is kind of silly because this all equals 1. This is 8, this is 8, this is clearly a midpoint. This one has to be midpoint too. So don't bother with this one. All you really need to say is 2x plus 1 equals x squared minus 7. So now it's going to be quadratic time. Let's say 0 equals x squared minus 2x, that's plus 1. Okay, I can read my handwriting there. Minus 8, and let's solve that in the calculator. All right, so I just opened up a calculator page, go algebra solve, and then I type it in, and don't forget at the end of that to type, oh, sorry, it's drifting around, comma x, because it needs to know which variable you mean, and sorry, you can't see that. I get x is -2 or x is +4, and you have to give both those answers. So x is either, what did it say, -2 or +4? I like to write it this way, -2 or +4. Okay, that's all for this time. I will see you in class.